Complexity is the enemy of security. Opening, the security team nobody could find. There is a company, mid-sized, 12 years old, successful enough, that employs a dedicated security team of 8 people. Those 8 people spend the better part of every week doing something that, from the outside, looks like security work. Reviewing firewall rules, managing patch exceptions, responding to alerts, attending vendor calls. But if you sit next to any of them for a full day, what you notice is that almost none of that time is spent on actual threat analysis or risk judgment. Most of it is spent navigating the system, figuring out which of the 14 security tools has the log you need, translating the output of one tool into the format that the next one expects, tracking down who owns the exception that was created 3 years ago by someone who has since left the company, and reconciling the different alert severity scales used by 3 separate products that all claim to measure the same thing. Ask the security team why they have 14 tools, and the answer is always the same. Each one was added to solve a specific problem that the previous ones did not cover. At the time of each purchase, the decision was rational. A new product category emerged. A penetration test exposed a gap. A compliance requirement pointed to a control that did not exist. Each tool made sense individually. Collectively, they created an environment that is harder to monitor, harder to understand, and harder to operate than the threat it is supposed to defend against. The attackers, operating from the outside, have a simpler view of the target than the defenders who are supposed to know it. This is what it means to say that complexity is the enemy of security. Not that sophisticated systems cannot be secured. They can. Not that mature environments should remain primitive. They should not. What it means is that every layer of complexity you add to a system introduces proportionally more surface area for failure. More configurations that can drift, more integrations that can break, more exceptions that can accumulate, more decisions that can be made inconsistently. And the most insidious quality of complexity is that it tends to be invisible. You do not feel the security debt accumulating the way you feel the exhaustion of an overworked team. You feel it only when something breaks, and by then the complexity has usually had months or years to compound. This session is about developing a practitioner's instinct for recognizing complexity in an architecture, in a process, in a set of security rules, and understanding what it costs, why it builds up, and how to make the case for simplification in the language that actually gets it resourced and acted on. That instinct is rarer than it should be. And in an interview room or a design review, it is what separates someone who knows security from someone who can actually practice it. The foundation, what economy of mechanism actually means. The principle known as economy of mechanism is one of the oldest ideas in the formal study of security design. Jerome Salzer and Michael Schroeder articulated it in 1975 in their landmark paper on the protection of information in computer systems, and its core statement has not aged at all. Keep the design as simple and small as possible. Every component you add to a system is a component that can fail, be misconfigured, or be exploited. The principle is not arguing for primitive systems. It is arguing that complexity should be justified, that every additional moving part should earn its place by providing security value that cannot be achieved another way, and that when simpler alternatives exist, they should be preferred precisely because simplicity is itself a security property. The trusted computing base is where this principle has the most concrete technical expression. The TCB of a system is the totality of protection mechanisms, the hardware, firmware, and software that must work correctly for the system's security policy to be enforced. Everything outside the TCB can, in principle, misbehave, and the security guarantees should still hold because the TCB remains correct. The implication of this architecture is that the TCB should be as small as possible. A TCB that is small can be reviewed thoroughly, tested rigorously, and reasoned about with precision. A TCB that has grown to encompass thousands of lines of code and dozens of interacting components cannot be fully understood by any individual, which means it cannot be fully trusted. The size of the TCB is not just a software engineering concern. It is a direct measure of how much complexity you are being asked to trust. This connects to one of the most important distinctions in governance: the difference between a policy, a standard, a guideline, and a procedure, and why the failure to maintain these distinctions is itself a complexity problem. A policy is a statement of organizational intent. What must be protected, at what level, and why. A standard is the specific, measurable technical requirement that gives the policy its implementable substance. A guideline is an advisory recommendation for situations that the standard does not prescribe. A procedure is the step-by-step instruction for how to execute a specific task in compliance with the standard. When organizations conflate these layers, when policies are written with the specificity of procedures, when standards are treated as optional guidelines, when procedures differ by team or by individual, the result is a governance environment that is more complex than the system it is supposed to govern. Different teams interpret the same policy differently and implement it differently, which means the security controls are inconsistent even when the policy documentation looks uniform. The diagnostic symptom of this problem is exactly what one of our troubleshooting scenarios describes. Different departments interpret a framework like the NIST CSF inconsistently, leading to duplicated controls in some areas and complete gaps in others. The root cause is usually not that the framework is ambiguous. It is that the organization never translated the framework into concrete, specific standards that left no room for interpretation. The distinction between stateful and stateless protocol design is worth examining here because it illustrates how complexity enters at the protocol level and produces security consequences that can seem unrelated to their cause. A stateful protocol maintains context across multiple interactions. The server remembers who you are, what you have done, and what state the session is in. A stateless protocol treats every request as independent. Each request must carry all the information needed to process it, and the server maintains no memory of prior interactions. From a security design perspective, stateless protocols are generally simpler to reason about, simpler to scale, and simpler to secure, because there is no session state to be hijacked, no state machine to be driven into an unexpected condition, and no server-side memory to be corrupted or confused. The trade-off is that stateless designs can produce larger individual requests and require the client to manage more context. REST APIs built on HTTP are largely stateless. Kerberos and many enterprise authentication protocols are deeply stateful, which is why Kerberos troubleshooting, as any enterprise administrator will attest, involves tracking down ticket states, clock drift, and ticket-granting service interactions that are invisible unless you know exactly which log to look at. Neither design is wrong, but the security implications of a statefulness choice are real, and they need to be made deliberately rather than inherited by accident. The structural tension, completeness against comprehensibility. The central tension that complexity forces into every security decision is this. The more complete your coverage, the harder your environment becomes to understand. And the harder your environment is to understand, the more likely it is to contain the gaps that completeness was supposed to prevent. Consider firewall rule management as a concrete illustration. A new network is built. The initial firewall rule set is clean and logical. 20 rules, each one clearly named, each one tied to a documented business requirement, each one reviewed by the team that added it. Over 3 years, through organic growth, vendor integrations, project deadlines, and the inevitable accumulation of exceptions, the rule set grows to 900 rules. Many of those rules are duplicates. Some are contradictory. A significant number reference systems that no longer exist. Some were added as temporary exceptions during an incident and never removed. The firewall is not providing less security than a 20-rule firewall in any individual rule. But the aggregate effect is that the team cannot accurately describe what the firewall allows and denies without running a dedicated audit that takes weeks. An attacker who can probe the firewall systematically can build that picture faster than the defenders can maintain it. The completeness of 900 rules has produced less security than the comprehensibility of 20 well-understood ones. This dynamic appears at every layer of a security architecture. An identity environment that started with 50 Active Directory groups and grew to 3,000 over a decade is an identity environment where no administrator can tell you, with confidence, who has access to what. An alert correlation rule set that started with 40 CM rules and grew to 400, with no retirement process for rules that stopped producing value, is an alert environment where the signal-to-noise ratio has degraded to the point where analysts cannot sustain attention on genuinely important alerts. A RBAC configuration that was initially built around clear role definitions and grew to accommodate individual exceptions. Just give John access to this one thing for this project. Is an access control model that can no longer be described as role-based in any meaningful sense, because the roles have been eroded by the accumulated weight of individual permissions that do not conform to any role. The tension is not between good security and bad security. It is between two different failure modes. The failure mode of insufficient complexity is obvious. A system without enough controls has gaps that attackers can exploit directly. The failure mode of excessive complexity is invisible until it is catastrophic. A system with too many controls has gaps that nobody can see because no one fully understands the system. The first failure mode gets you breached through what you did not build. The second failure mode gets you breached through what you built but could no longer manage. The practitioner's skill is learning to see both failure modes simultaneously when evaluating an architecture, rule set, or process design. The question is never just, does this provide coverage? The question is always, does this provide coverage that we can actually understand, operate, and maintain over the time horizon we care about? Architecture. What simplicity looks like when built deliberately. When simplicity is treated as a design goal rather than an accidental outcome. The architectural choices that follow look different from those produced by an incremental add-as-needed approach. The three-tier web architecture, web tier, application tier, database tier, is one of the best examples of complexity management built into a structural pattern. The separation into three tiers is not primarily about performance or scalability, though it serves both. It is about making the security boundaries explicit and manageable. The web tier accepts untrusted external traffic. The application tier processes business logic and talks to the database. The database tier holds the data and talks to nothing outside the application tier. These are three fundamentally different trust zones, each with a different security posture and a different set of appropriate controls. By making the separation physical, by putting the tiers in different network segments with firewall rules that enforce the communication boundaries, you make it impossible to accidentally collapse those zones through a misconfiguration, and you make it immediately visible when traffic is attempting to cross a boundary it should not. Contrast this with a flat architecture where all three tiers run on the same server or the same subnet. The same controls still need to be applied, but now they have to be applied in software rather than in network topology, which means they're more likely to drift, more likely to be inconsistently enforced, and much harder to verify without detailed inspection of every running process. Role-based access control, implemented correctly, applies the same principle to identity. The correct structure for RBAC in an Active Directory environment is a clean mapping from organizational roles to permission groups. An HR analyst role maps to a specific group, that group maps to specific resource permissions, and everyone who holds that organizational role is a member of that group and no other. The implementation cost of this structure is an upfront investment in defining the roles carefully and resisting the organizational pressure to make exceptions immediately upon deployment. The operational benefit is that access management becomes comprehensible. When an HR analyst's role changes to HR manager, you move them from one group to another rather than hunting through every system they have ever accessed to find and update individual permissions. When you need to answer the question, who has access to the payroll database? You look at the membership of the payroll data access group, and you have your answer in seconds rather than days. The complexity that RBAC eliminates is not the complexity of the permissions themselves. The underlying permissions exist regardless of how you manage them. It is the complexity of the decision-making involved in determining who should have them. Role definitions make that decision once, at the policy level, for every person who holds that role, rather than making it individually and differently for every employee who ever requests access. The infrastructure as code approach, using tools like Terraform to define cloud and on-premises infrastructure in versioned, reviewable code rather than through manual configuration, is perhaps the most direct architectural expression of the principle. A manually configured environment accumulates complexity in the gaps between what was intended and what was actually deployed, in the undocumented exceptions that live only in one administrator's memory, and in the configuration drift that occurs when systems are patched, updated, or modified without following a documented change process. An environment defined as code has none of those gaps, because the code is the authoritative description of the environment. If a change is made that deviates from the code, that deviation is immediately visible. If 15 AWS accounts need to be configured with the same security baseline, the same code is applied to all 15, and any deviation in any account is flagged by the same verification process that catches deviations in the others. The standardization that IAC produces is not a side effect of the approach. It is the security feature of the approach. Tools that enforce simplicity. 4 tools represent different dimensions of complexity management, and each one has costs and limitations that make it a decision rather than an obvious choice. Single sign-on addresses identity complexity at its most fundamental level. In an organization without SSO, every application maintains its own authentication mechanism, its own credential store, its own session management, its own password policy, its own MFA configuration. 50 applications mean 50 places where an employee's identity is represented, 50 places where a compromised credential can be used, 50 places where an offboarding checklist item can be missed and leave an ex-employee's account active. SSO consolidates those 50 representations into one. The employee authenticates once to the identity provider, and all applications trust the token the IDP issues. From a security perspective, this consolidation is almost entirely positive. One authentication event instead of 50 means one place to enforce MFA, one place to apply conditional access policies, one place to detect anomalous login behavior, and one place to revoke access immediately when someone leaves the organization. The cost is the architecture required to support it. The IDP must be highly available and well secured because it is now the single point of both trust and failure. A brief outage of the IDP is a brief outage of every application that depends on it. A compromise of the IDP is a compromise of every application that trusts it. These risks are real, but manageable with proper redundancy and hardening. The limitation that often goes unaddressed is the legacy application problem. Applications built before modern identity standards like SAML and ODC were common may require additional integration work or cannot participate in SSO at all. Those applications remain outside the simplified identity environment, which means the simplification is incomplete until the legacy gap is closed or the legacy application is retired. SIEM log normalization deserves particular attention because it is the dimension of complexity management that most directly affects the analyst who is trying to do their job under pressure. A SIEM that ingests logs from 50 different sources, Windows event logs, Linux syslog, firewall traffic logs, cloud provider API logs, EDR telemetry, web server access logs, without normalization presents those 50 different sources in 50 different formats, with 50 different field names for the same concepts and 50 different timestamp formats and 50 different severity scales. The analyst who is investigating an incident that spans multiple log sources has to simultaneously understand all of those formats, mentally translate between them, and maintain coherent investigative context while doing so. The cognitive load is enormous and the error rate is high. A SIEM that normalizes all incoming logs to a common schema. The Elastic Common Schema or the AWESOME framework are widely used examples. Means that a source IP address is always called source to IP regardless of whether the log came from a firewall or a web server. That timestamps are always in UTC in the same format, and that severity levels are always expressed on the same scale. The analyst investigates across log sources without switching mental models. The cost of normalization is the upfront investment in building and maintaining the parsing rules for every log source, and the ongoing cost of updating those rules when vendors change their log formats. The limitation is that normalization inevitably loses some fidelity. The fields that exist in one log format but have no equivalent in the common schema are either dropped or mapped imperfectly, and those edge cases occasionally matter in an investigation. Infrastructure as code, which we encountered in the architecture section, deserves additional examination as a tool rather than just a philosophy. Terraform, in practical deployment, enforces simplicity through the principle of declared state. You describe the desired state of your infrastructure in code, and Terraform figures out what actions are required to reach that state from the current state. This means that a security configuration drift, an S3 bucket that was manually made public, a security group rule that was added through the console, shows up as a delta between declared state and actual state, and Terraform will report it and offer to correct it. The cost of this model is the discipline required to maintain the IAC as the single authoritative source. If administrators are making changes both through Terraform and directly through the console, the declared state and the actual state diverge in ways that can be confusing to resolve. The limitation is coverage. Some infrastructure decisions are genuinely complex enough that expressing them purely as declarative code requires significant engineering investment, and teams under delivery pressure will sometimes reach for manual configuration rather than invest in making the IAC robust enough to handle the edge case. Managing those exceptions carefully, documenting them, tracking them, and creating a path to bring them back under IAC is the governance work that makes the tool effective over time. Containers, specifically the Docker and Kubernetes ecosystem, reduce complexity through a specific mechanism that is worth naming precisely. They minimize the dependency surface of each deployed application. A traditional application deployed on a shared server has access to, and is at risk from, everything on that server. Other applications, libraries, system-level configurations, services that have nothing to do with the application but that run on the same OS. A containerized application packages exactly what it needs and runs in isolation from everything else on the host. The attack surface of the container is limited to the application's own code and its declared dependencies. This is not a complete security solution. Containers share the host kernel, which means a kernel vulnerability can potentially be exploited to escape the container's isolation boundary, and the orchestration layer introduces its own attack surface. But it is a meaningful reduction in the scope of what needs to be secured per application. The cost is the operational overhead of building, managing, and securing the container infrastructure itself. Container image scanning, registry security, Kubernetes RBAC, network policy between pods, and runtime security monitoring are all new capabilities that must be built and maintained. The limitation that catches organizations by surprise is that containerization does not automatically simplify the application's own internal complexity. A monolithic application with a complex, poorly understood code base does not become simpler because it runs in a container. It becomes isolated, but isolation and simplicity are different properties. Implementation. The work of simplification in practice. Two implementation scenarios are worth working through fully because each one reveals a different dimension of what simplification actually requires when you're operating inside a real organization with real constraints. The first is the challenge of building a CM that produces actionable signal rather than overwhelming noise. The brief description, ingest logs, write correlation rules, build dashboards, conceals the actual implementation problem, which is that a CM that ingests everything without discrimination does not produce clarity. It produces a different kind of complexity. Instead of 15 separate tools with 15 separate interfaces, you have one tool with 15 streams of raw data that have not yet been made meaningful. The implementation begins before any log source is connected, with a decision about what questions you need the CM to answer. These questions come from your threat model. What attack patterns are most likely against your specific environment, from the threat actors most likely to target your industry? The questions determine which log sources are high priority. An organization worried about credential-based attacks needs authentication and identity provider logs before it needs DNS query logs. This prioritization prevents the common failure mode of ingesting everything at once and producing 400 correlation rules the team cannot maintain. Normalization follows, and it is more technically involved than it sounds. Every log source requires a parser, a set of rules that extract structured fields from raw text and map them to a common schema. A Windows login event and a VPN authentication event from a completely different vendor both produce the same normalized fields: user.name, source.ip, event.action, event.outcome. Writing those parsers requires someone who understands both the original format and the destination schema, and that parser library must be maintained as vendors update their formats without warning. The correlation rules that follow are where analyst judgment gets embedded into the system. A rule that fires on a single failed login is noise. A rule that fires when a single source IP produces more than 30 failed logins against 3 or more accounts in 10 minutes. And at least one of those accounts then authenticates successfully from the same IP. Describes a credential stuffing attack with enough specificity to be both accurate and actionable. The specificity of each rule determines its signal-to-noise ratio, and the aggregate signal-to-noise ratio of the rule set determines whether the SIEM is a security asset or a distraction. The second implementation scenario is RBAC and Active Directory for an organization with departments including HR, finance, IT, and sales. The implementation decision that most teams get wrong is the group structure, and the error is predictable. They create groups based on permissions rather than based on roles. The result is a group called Finance File Share Read Write, and another group called Payroll System Admins, and another group called Expense Report Approvers, and 3 years later, nobody can tell you which combination of groups the CFO should be in, because the groups describe system permissions rather than organizational roles. The correct structure starts with organizational roles rather than system permissions. The finance department has roles: finance analyst, finance manager, finance director, finance system administrator. Each of those roles has a defined set of access requirements that comes from the job description and the business's risk assessment of what that role should and should not see. The finance analyst role needs read access to the shared finance drive, access to the expense reporting system, and access to the budgeting tool. The finance manager role needs those same things plus write access to specific budget files and access to the payroll view that the analyst should not have. Those role definitions become groups: finance analyst and finance manager. The group memberships are managed by HR during onboarding and role changes. The system permissions are assigned to the group, not to individuals. When a finance analyst is promoted to finance manager, the HR system triggers a change in group membership, and that single change cascades correctly across every system that trusts those groups. The governance requirement that makes RBAC sustainable over time is an access review process. Group memberships drift regardless of how clean the initial structure is. People leave and their accounts are disabled, but group memberships persist. People change roles and old memberships are not fully removed. Projects end and temporary grants are never revoked. A quarterly or semi-annual review, in which each group's membership is confirmed by the business owner of that role, is the maintenance discipline that keeps the model accurate. Without it, complexity returns through accumulated exceptions and stale permissions, even if the original structure was correct. When simplicity was neglected, 3 diagnostic journeys. 3 failure scenarios illuminate different ways in which complexity produces security failures, and the diagnostic process for each one reveals the underlying simplification opportunity. The first scenario is a governance failure that has become visible, Different departments are interpreting the NIST cybersecurity framework inconsistently, leading to some departments with duplicated controls and others with control gaps. The security team is trying to reconcile the inconsistency and does not know where to start. The diagnostic begins with a mapping exercise, not a policy review. Pull the control implementations from each department and map them to the specific NIST CSF subcategories they are supposed to address. You're looking for two patterns simultaneously. The first is duplication. The same subcategory is implemented by two different controls in the same department, or the same subcategory is implemented by different controls in different departments that produce the same outcome through different mechanisms. The second is gaps, subcategories that are mapped to no implemented control in any department, or subcategories that are mapped in the documentation, but whose control implementations cannot actually be found or verified. When you find the inconsistency, the next diagnostic question is whether the root cause is ambiguity in the framework interpretation or ambiguity in how the framework was communicated to departments. The NIST CSF is deliberately high level. It describes what outcomes security control should achieve rather than prescribing specific implementations. An organization that distributed the NIST CSF to department heads and asked them to self-assess against it, without first producing an internal standard that translated the framework into specific, measurable requirements, created the inconsistency by design. Different department heads read the same framework language and made different reasonable interpretations. The fix is to produce a set of internal standards that map the framework to specific controls. For each NIST CSF subcategory that is relevant to your organization, the standard states, this subcategory is addressed by this specific control, implemented in this specific way, verified by this specific measurement. The measurement is what closes the interpretation loop. If the standard says that identified.am1 asset management is addressed by a quarterly scan of all production systems using the approved vulnerability scanner, a department either ran the scan last quarter or they did not. The binary measurement eliminates the ambiguity that was producing inconsistency. The second scenario is a CM that is generating thousands of false positive alerts from an internal vulnerability scanner. The scanner is correctly scanning the network. The CM correlation rule for port scanning is correctly detecting it. The result is that analysts are receiving hundreds of alerts per hour from a known, authorized source, and the cognitive cost of dismissing those alerts is eroding their ability to pay attention to genuine alerts. The diagnostic begins with a rule rather than the scanner. Pull the rule logic and ask three questions. What is it detecting? What is its detection granularity? And does it have a mechanism for distinguishing authorized from unauthorized sources? If the rule fires on any internal host that sends SYN packets to more than a threshold number of distinct destination ports in a time window, it is a correctly written rule that is being triggered by a correctly operating scanner. The rule's logic is not wrong. Its scope is too broad. The next question is whether the scanner's IP addresses and operating schedule are documented and stable. If the answer is yes, the scanner runs from these three IP addresses between these hours on this schedule. Then the fix is a suppression condition added to the rule. If the source IP is in the authorized scanner list and the time is within the authorized scanning window, suppress the alert. The suppression is not a bypass of the detection. It is a refinement of the detection that acknowledges that some port scanning is authorized and expected. The refined rule still fires when a source that is not in the authorized scanner list produces the same pattern, which is exactly when you want it to fire. The trap in this diagnostic is adding the suppression broadly. If you suppress all alerts from the scanner's IP regardless of what the scanner is actually doing, you create a blind spot. An attacker who has compromised the scanner host can exploit its scanning activity as cover for their own lateral movement, and none of it will be alerted. The suppression should be specific to the pattern that the scanner produces. Port scanning from the authorized IPs during authorized hours, rather than a blanket exclusion of all events from those IPs. Specificity is what makes the suppression a refinement rather than a gap. The third scenario is the complexity-driven secret leak. A critical API key used for threat intelligence enrichment has been accidentally committed to a public code repository. A developer added the key directly in the configuration file, pushed the commit, and the key was in the public repository for 6 hours before a team member noticed. The immediate response and the root cause investigation are two separate tracks that must run simultaneously. The immediate response begins with key revocation. Log into the Threat Intelligence Vendor's Management Console, revoke the compromised key, and generate a new one, and continues with an assessment of whether the key was used during the exposure window. Pull the vendor's API access logs for the 6-hour window when the key was public. Look for request patterns that differ from your pipeline's normal request volume, timing, or query types. A key that was discovered and used by an automated secret scanning tool will show a spike in requests, often from cloud provider IP ranges. A key that went unnoticed will show only your pipeline's normal usage pattern. The assessment determines whether the incident is a contained cleanup or an active threat requiring further investigation. The root cause investigation, running in parallel, asks why the secret was committed to the repository in the first place. The most common answer is that the developer was following the path of least resistance. The configuration file was the obvious place to put an API key because that is where other configuration values were, and no tooling was in place to prevent the commit from completing. The fix has 2 layers. The immediate technical layer is to deploy a pre-commit hook or a secret scanning tool in the CI/CD pipeline that detects patterns matching API keys, tokens, and credentials before the commit reaches the remote repository. Git hooks like GitLeaks or Talisman can be configured to scan stage files and reject commits that contain detected secrets. The structural layer is to move all secrets out of configuration files and into a secrets manager, HashiCorp Vault, AWS Secrets Manager, Azure Key Vault, and have the pipeline retrieve secrets at runtime from the vault rather than reading them from configuration. This removes the possibility of accidental commitment entirely, because the secrets are never in the files that developers handle. 3 roles, 3 encounters with the same enemy. 3 roles encounter complexity as an active threat at genuinely different moments, and each encounter demands a different kind of response. The security architect encounters complexity at the design table, in a specific moment when a stakeholder group is proposing to solve a security problem by adding a new tool. The meeting is going well. The new tool clearly covers a gap. The vendor's demo showed impressive capabilities. Every person in the room is nodding. And then the architect asks the question that tends to make the room uncomfortable. What will we retire when we add this? The question is not hostile. It is architectural. Every tool that is added to an environment is a tool that must be integrated, operated, updated, and eventually decommissioned. If the answer to what will we retire is nothing, Then the tool is being added to a stack that is growing without bound, and the complexity cost is being deferred rather than managed. The architect's specific skill in this moment is the ability to translate between the vendor's feature capabilities and the operational reality of the environment where those capabilities will be deployed. A tool that requires its own dedicated agent on every endpoint, its own log format parsed by the CM, and its own training program for analysts is not the same thing as a tool that uses the agent already deployed for EDR, normalizes its output into the existing schema, and fits into the analyst's existing investigation workflow. The former adds 3 new things to maintain. The latter adds 1. The architect is the person who can see both the capability and the cost, and who can articulate the difference clearly enough that the stakeholder group can make an informed decision rather than a feature comparison decision. The security data engineer encounters complexity in the gap between what the pipeline is supposed to do and what it actually does when the data coming in does not match the shape the pipeline expected. The specific moment is the one described by the multi-cloud log scenario. Flow logs arriving from 3 different cloud providers in 3 different formats, with different field names, different timestamp conventions, different IP address representations, and significantly different latency characteristics. The pipeline that was designed for a single cloud's log format begins to behave unpredictably. Some events arrive and are parsed correctly. Some arrive in formats the parser does not recognize and are dropped silently. And some arrive late enough that the CM's time-based correlation rules do not fire correctly because the events are being evaluated out of order. The diagnostic work requires understanding which of these failures is happening before attempting any fix. The engineer pulls the raw log samples from all 3 sources and runs them through the parsing logic manually, comparing the output against the expected schema. The fields that are missing from a normalized output reveal where the parser is failing. The timestamps that are out of order reveal which log source has the latency problem. With those 2 pieces of information, the fix is straightforward in principle. Add parser rules for the unrecognized fields, add a time buffering step that holds events and sorts them before submitting them to the CM. But it requires the engineer to build and test the changes against representative samples of all 3 log formats, not just the one that was the most recently added. The unified logging pipeline, when it is working correctly, is a significant simplification for every analyst who consumes its output. But it is only simple for the consumer if it is robustly engineered at the point of ingest, and that engineering investment is ongoing rather than one time. The security automation engineer encounters complexity in the moment of the production incident, when the automation that was supposed to simplify and accelerate the process has done something unexpected at scale. The trailing comma in the JSON report file is a small but representative example. A manual edit introduced a syntax error that the automation pipeline did not catch before delivering the malformed output to the dashboard consuming it. The consumer, in this case the JavaScript on the dashboard, fails with a parsing error and the dashboard goes dark. The incident is not a sophisticated attack. It is the inevitable collision between human-introduced complexity and automation that assumed clean inputs. The fix has 2 layers, and both need to be implemented before this engineer's work is done. The immediate fix is output validation. Every file that the pipeline produces is validated against its expected schema before it is committed to the output location. For JSON files, this means running a JSON linter against every generated file as the last step before the file is moved to its final destination. A file that fails the linter does not reach the consumer. The pipeline logs the failure, raises an alert, and terminates rather than delivering a broken artifact. The structural fix is eliminating the conditions that made the manual edit possible in the first place. If the JSON file was edited manually because the pipeline did not have a mechanism for updating it programmatically, the appropriate response is to build that mechanism, not to protect against the manual edit with validation alone. Validation catches the error. Removing the need for manual editing prevents the category of error. Both layers together are the complete response. Case scenario: the 15-brand security consolidation. You're the head of security for a media holding company that owns 15 separate brands. Each was originally an independent business acquired over a decade, and each operates its own technology stack, its own AWS account, its own identity provider, its own endpoint protection vendor, its own firewall platform, its own log management tool. 3 of the brands have no dedicated security staff. 2 have programs that would be considered mature. The rest are somewhere in between, each with their own definition of what secure means. The central security team, 6 people covering 15 brands, is failing. Not because they lack skill, but because the environment is too complex for 6 people to understand coherently. When an incident occurs in Brand 7, the team must first locate which identity provider Brand 7 uses, find administrative credentials, determine which log source to query, and confirm which analysts have access to it. By the time the investigation begins, the attacker has had an additional 30 to 40 minutes uncontested. The complexity of the environment is directly measurable in mean time to respond. The constraint shaping the consolidation project is financial and organizational. The board has approved a consolidation budget that covers 18 months at a figure significantly smaller than a full infrastructure replacement. Each brand's leadership also has contractual autonomy over technology decisions, which means every consolidation action requires negotiation rather than directive. The project begins with prioritization because the budget and timeline do not permit consolidating everything simultaneously, and doing so would be counterproductive even if the budget allowed it. The first consolidation target is identity, because a single identity provider is the highest leverage change available. It eliminates the 15 separate credential stores, makes MFA enforcement consistent and auditable, and creates a single revocation point for every compromised account across the enterprise. The technical migration, moving all 15 brands to Azure AD with federated authentication, takes 11 months. The organizational negotiation takes most of those 11 months because several brand technology leaders have concerns about operational dependency on a central system and need to understand the redundancy architecture before they will sign off. The resolution is to demonstrate the failover configuration in a stage test that simulates an identity provider outage and shows that brand operations continue without interruption. The demonstration is more persuasive than the documentation. The second consolidation target is log collection, because the security team's investigation capability depends directly on having a consistent, accessible view of events across all 15 brands. Rather than migrating all 15 brands to a single CM, which would require replacing 2 existing mature CM deployments that brand teams rely on and trust, the architecture decision is a log aggregation layer that collects from all 15 sources, normalizes to the elastic common schema, and makes the normalized data available in a central platform for cross-brand investigation. Brand teams can keep their existing CMs for their own operational use. The central team gets a unified view for enterprise-level investigation and threat hunting. The trade-off is that this architecture requires maintaining the parser rules for all 15 existing log formats. And anytime a brand vendor updates their log format, the parser must be updated. A dedicated team rotation for parser maintenance becomes a standard operational task rather than an ad hoc response. The infrastructure standardization comes third because it is the highest cost and highest disruption effort. The decision is not to replace all 15 infrastructure configurations with a single Terraform template immediately. Instead, a golden path template is created, a reference AWS account configuration that meets the security baseline, defined in version Terraform code, tested against the security requirements, and documented clearly enough that any brand's infrastructure team can implement it. New projects at any brand must be built using the Golden Path template. Existing infrastructure is migrated to the template as part of routine infrastructure refresh cycles rather than on a forced migration schedule. Deviations from the template are permitted but must be documented, approved by the central security team, and reviewed annually as formal risk acceptances. At the end of 18 months, the attack surface is dramatically reduced. Not because every exception has been eliminated. There are still legacy applications at 4 brands that cannot participate in the SSO consolidation without vendor support that has not yet been scheduled. Not because all 15 brands have identical infrastructure. The Golden Path has been adopted for all new projects, but some legacy infrastructure remains in place. But the central security team can now investigate a cross-brand incident in minutes rather than hours, because they have a single identity platform to query, a single normalized log source to search, and a consistent infrastructure baseline to reason about. The complexity that remains is documented and managed. The complexity that was eliminated was invisible and unmanaged. That distinction is the measure of what the consolidation accomplished. Closing, the discipline of enough. There is a question that is rarely asked in security meetings, but that the complexity principle demands you learn to ask in every one of them. Is this the simplest design that provides adequate protection? Not the most comprehensive design, not the most feature-rich design, not the design that addresses every theoretical attack scenario. The simplest design that provides adequate protection for the specific assets, in a specific threat environment, for the specific organization that must operate and maintain it over the years ahead. The discipline this question requires is harder than it sounds, because every instinct in security culture pushes toward more controls, more coverage, more visibility, more tools. More feels safer. More feels professional. More is easier to justify when something goes wrong. We had 14 controls. The attacker found a gap in the 15th area. The defense of more is always available after a failure. But the failures that complexity causes are rarely attributed to complexity. A SIEM that nobody can tune effectively because the rule set is too large is described as an analyst capacity problem. An identity system that nobody can accurately describe is described as a visibility problem. A firewall rule set that contradicts itself is described as a change management problem. The root cause, that the system has exceeded the cognitive capacity of the team to operate it correctly, is invisible until someone is willing to look at the whole and ask whether the whole makes sense. The posture that this principle is asking you to develop is the willingness to advocate for less, on the grounds that less, when it is the right less, designed deliberately and maintained rigorously, is more secure than more that cannot be understood. That is not a concession to resource constraints. It is a recognition that security is ultimately a property of comprehensible systems, and that the most important security question about any design is not whether it provides coverage, but whether the people responsible for it can actually understand it well enough to trust it. Build systems that the team can reason about. Eliminate everything that cannot justify its place in that reasoning. And resist every single day the organizational pressure to add without retiring. End of session. Complexity is the enemy of security.